Hello, and let's get started with lecture 5. So one of the things that you need to be able to do from a technical point of view when you're doing canonical quantization, this procedure we've been looking at, is to manipulate these commutators that appear all over the place. So we're going to see that a lot in this lecture when we work through various expressions where you have to manipulate these commutators. And we're also going to get to an important and interesting result because we're going to construct the Hamiltonian. So we'll see that Hamiltonian that we find is not totally straightforward. We need to think a little bit more carefully about it. Okay, so let's start by just reminding you of where we've got to. So we've found our quantum field. We're expressing it in the Heisenberg picture in the sense that it has time dependence. And we've done this expansion of the field in terms of raising and in terms of lowering operators. Okay, that's our lowering operator, minus I, and we have the 4-vector dot product, minus I dot kx, plus raising operator, the raising operator, the plus I k dot x. And well, so I suppose I should define what omega k is. And so we're taking omega k to be k squared plus m squared. Okay, so the first thing we should do, so we have an expression for phi, but we don't have an expression for this pi field. First thing we should do is to find our pi expression. So we know what the classical expression is. So we get it from differentiating the Lagrangian with respect to the time derivative. So it's phi dot. Okay. So we're going to find that our momentum field is also phi dot. So I'm going to take the time derivative with respect to t of the expression above to get an expression conjugate momentum. Okay, so let's do that. It's not too tricky. So it's a combination of terms that has no time dependence, just comes along for the ride. Okay, and then we need to differentiate the term in the brackets above. So remember, all of the time dependence has been put into these exponential factors. So the only bit that we have to worry about are the exponential factors. So we will get a factor of minus I omega k from the first term when we differentiate with respect to time, when we differentiate this exponential, and we'll get a factor of plus I omega k from this second exponential term that we have in the expression. Okay, so we can simplify this a little bit. d3k cubed, and then I'm going to pull out the factor of minus I, and I'm going to write omega factors as omega k over 2, rather over root 2, ak and here we'll get a minus ak dagger. Okay, so this is our expression. This is our expression. Great. So next, we want to turn to consider the properties of our raising and lowering operators a little bit further, okay? So one thing we know is what the commutation relations are for the pi and the phi fields, or phi with pi with pi, and pi with phi. So just to remind you in a very shorthand, so these were equal time. Very quick, remind you this sort of schematic form. So these should end these have to be evaluated at the same time. So we have the pi commutators with another pi is 0. Oh, sorry, phi with phi is 0, pi with pi is 0. The non-zero one is x and y. And this gives I delta 3 x minus y. Okay, so what we would like to find is the set of commutation relations that must be satisfied by AK and AK dagger. Let's go ahead and do that. So we can get those by expressing our AK and AK dagger fields in terms of fields that we know the commutation relations of, so namely in terms of the pi and the phi fields. So we can see how this might work, where, since we have this minus sign in this expression, so you'll see that some combination of the phi fields, where we have a plus sign in front of the A dagger, added to some combination of the pi field. We need the right factors to cancel these omega k terms, but straightforward to figure out. But when we add these together, we'll end up with a term that only depends on AK. Be able to cancel those combinations. So express, as I said, our fields in terms of the things that we know the commutators of, so the phi and the pi. And as I said, it's just a case of adding some combination of phi and pi together. So you write down what the result is. So if you add root 2 omega k, it's phi. In the labels x and t, plus the combination 2 over omega k. You need to have a factor of I times our field I, x, and t. We will get this combination. So 2 times d3k ak, we have e to the minus I k dot x. Okay. We've just got the e to the minus I k dot x terms, and we need to still have these d3k pieces. Okay. But we can just apply the inverse Fourier transform to find out what AK is going to be in terms of these fields. So what we have to do by the inverse transform follows. So we'll have A. The inverse transform is going to be an integral over d3x. And I've got this factor of a half. And with the convention I'm using for my Fourier transforms, I put all of the pi factors on the k integral. So there's a 2 pi cubed term here. So there's no 2 pi factors when I do my inverse transform x. And then I have all of the left-hand side of the term above. And then I need the exponential factor, and the exponential factor is going to be e to the I k dot x. Okay, so here I'm using the, again, the 4-vector dot product. So you might pause for a second and go, well, wait a second, you're doing a 3-dimensional Fourier transform, so why, what's going on? So that's correct. I am doing the inverse of the 3-dimensional Fourier transforms. So from the Fourier transform, I get to the e to the I 3-vector k dotted into 3-vector x, and I just pull across I multiply across the e to the I omega t factor. Okay, so I end up again with an e to the 4-vector I k dot x. So this is a valid, legitimate result. So typically we simplify this a little bit. So we'll write d3x, have the omega k for 2 factor pulled out the front, and we simply have phi t, and we end up with a factor of I over omega k field e to the I k dot x. Okay, so this is then a useful expression that we can use. So this is our AK operator in terms of the fields that we know the commutation relations of, and we have these extra things floating around, so the e to the ikx and this omega k factor. Okay, so I'm not going to go through the procedure for the dagger, but needless to say, it's the same, or at least the same approach. The result is simply the Hermitian conjugate. So our factor of plus I goes to minus I. Our exponential will go to a minus ik dot x. Good. So we can express these fields in terms of pi and phi. Great, we've done that. What we'd like though is to figure out commutation relations involving A and A dagger. Okay, so we're going to use our expressions together with the commutation relations that we know for the phi and the pi fields. Let's work one of them out. Show you how these calculations proceed. So let's do AK with AP dagger. Okay. So what we want AK, AP dagger. And we can substitute in the expressions that we had. Okay, so we're going to have integrals over our position variables. So for the AK term, I'm going to do it over d3x, and for the AP term, I'm going to use a separate label. I'm going to do it over d3y. So I'm going to end up with an integral d3x, d3y factor. And I'm going to have these omega k factors that are out the front above. Okay, so for the AK term, I'll end up with an omega k over root 2, and for the AP, I'll end up with an omega p over root 2. So I'll write this as omega k, omega p over 2. I should probably do 2 times 2, which is 4. I'll keep it inside. A bit more obvious, I'll keep it inside the square root. I could take the square root of 4 if I wanted, but let's leave it as it is. Okay, and then we want to do a commutator. So the commutator is the rest of the. Let's use this notation I used earlier to simplify my life a little bit. So let's write phi x. So this is shorthand for this term, plus I over omega k I x. Pi x is shorthand for pi xt. Then we need to do the commutator, or we need to put the expression for AP dagger into my commutator. So I'm going to have a phi, but now I'm going to use the label y. So remember, I'm using the position label y to go along with my p. Go along with my p operator. We have a minus sign over omega k. And then the final thing we have to remember is to include these exponential factors. So we're going to have e to the I a dot x, not put a 3 vector on it, it's a 4 vector. And we have an e to the minus I p dot y. Okay, so now it's just a case of grinding through these commutator relations. Okay, so there's a useful result that you can use for commutators. Let's remind ourselves of the results for the commutator of a plus b with c plus d, because obviously we have the form a plus b and c d here. Okay, so there's some rule, which is that this can be broken into 4 commutators. Just have this combination. Now it's a case of just working through these 4 options. So let's do the commutator bit. Let me look at this bit. That here. Bring all of the other factors along later. I'm just going to focus on this commutator. So the 4 terms we will get, so we'll get phi x. So A is going to be phi x. C is obviously going to be phi y. Okay, and let's just work through. So we have A with D. So D is obviously going to be this combination, so minus I over omega k I y. Then we have B with C. Let's even, I want to keep it clean, so I'm going to leave the hats off expressions because it's already a lot of terms floating around. So we're doing B with C, so it's this, and then we have B with D. Okay, so some of these, 2 of these commutators we can get rid of immediately because, so here's kind of the schematic form, the pi with pi and the phi with phi, so these 2 are both going to be equal to 0. Okay, so down below we can kill 2 terms, 1, 2. So the only interesting ones are the 2 in the middle. Okay, so we're going to have a minus I, so let's pull out the minus I omega k factor from the commutator. And I realized, yeah, okay, good. One extra thing, I realized I've made a mistake up here. Well, I don't know if you spotted it. This should not be an omega k here because this is the omega that's associated with the p expansion. So this should clearly be an omega p. So let's correct that. P. And then that was the d term, so that enters in anywhere where there's a y. Okay, so it's technically over here, but that term is 0 anyway. Okay. So we have a minus I over omega p piece then with pi x and pi y. And then we have plus I over omega k, so this really isn't omega k, x phi y. So now we use the result that we had above, back, that's equal to I times the delta function. Minus I over omega p times I with a delta function, x minus y. The first term, second term, because the commutator order is swapped, we'll get a minus I factor, and I'll still write it as d3x minus y. It's the delta function doesn't care if it's x minus y or y minus x, it's the same. So we can simplify this a little bit, because minus I times I is obviously 1, and we have that in both expressions. So we have a 1 over omega p plus 1 over omega k times a 3d delta function. Okay, so that is what this commutator bit simplifies to. So something with a delta function and a 1 over omega p and a 1 over omega k. So that's, okay, let's rewrite the expression again. So we have it on the screen. So we're going to have a d3x, a d3y. We had a p over 4, and then we had these exponential factors. So it's I k dot x minus p dot y, and then we had the commutator. The commutator we've just worked out, so it's 1 over omega p, 1 over omega k, delta 3 x minus y. So this is nice because we can get rid of this delta 3x minus y by integrating over one of the variables, or over one of these d3x or d3y. So let's make a choice. So we could do d3 rid over d3y, and we'll leave behind d3x. So we're going to have e to the I, let's write it as k dot x minus, let's do it as p dot x. So actually we have to go back and just double check time component, okay, because our delta function here is operating on the spatial bits. Got a 4D piece in here. So let's just go back and double check one thing. Okay, so we can actually, yeah, we're going to have, yeah, good. So we want to have, so we labeled our lowering and raising operators with different variables, x and y here, to avoid confusion. But we didn't have to say anything about the time coordinate here. So the time coordinate doesn't enter. So we can, this time coordinate in here will actually be the same. So a little bit subtle thing going on here. Do it in a different color. This color, I hope you can see. So this e to the I k dot x is shorthand for e to the I, positive, not a negative, it's e to the I omega k t minus k dot x. And the e to the minus I e dot y term, e to the minus I omega p t, put in the brackets, minus p dot y. Okay. Okay, so the important point is, well, the omegas are different, but the t coordinates can be the same. Okay, so this is going to help when we, this means that we really can simplify. So what this delta function has done is now set the spatial coordinates to be the same and the time coordinates are the same. So we can actually simplify this exponential and write it as k minus p dot x. K minus p dot x. Okay, and when we do that, we can actually see we can simplify it a little bit further. So one thing that you should remember is, just check. One thing I should also remember, I'm just trying to look back for inspiration about the sign of it, but we have, let me write it down. I guess the sign doesn't matter in the end. So we'll have e to the I, I suspect it might be a minus, but so I'd have to, it may be plus or minus here. It doesn't matter in the end because I think it might even be either, in fact. But anyway, the important point is that when we integrate this exponential over d3x, we get another delta function. So this becomes a delta 3k minus p. So the sign in front doesn't matter because k minus p and p minus k, the delta functions are the same. So we can do that in the integral above because the only x dependence does enter from this exponential term. So that's use that in the expression above. Okay, so we're going to have, again, we're only integrating over d3x. So let me start by writing down what the time component is, because the time component isn't integrated, but is the bit that we have integrated is the e to the minus I k dot p dot x term. So that's the bit that we're going to integrate over d3x, and that's the bit that we're going to then replace with our delta function. Let me just do the replacement. At this point, so it's 2 pi cubed 3 k minus p, and then we have all of these omega factors that we have to deal with. So we've got the omega k, we've got the omega p, we've got a factor of 4, plus these other terms. Okay, so this kind of looks like a nice expression. Well, it does look sort of nice. So naively, you might have thought, well, it is just going to be some delta function normalization, or the commutator is just going to end up with some delta function. We've got the delta function, but we have all this other stuff as well, right? We've got the exponential factor. We have these, got the omega k, omega p over 2. So I've now done the square root of 4. We have all of this stuff. So the question is whether or not we can simplify any of these, or do we always have to carry around all of this stuff in our expressions? The answer is we can simplify it, and in fact, it's all going to simplify down to 1. So let me explain why that's the case. Okay, so in practice, where anytime you actually use these commutators, it'll typically appear in some integral expression, and in an integral expression, what will happen is that you'll integrate the delta function, and the delta function will force, delta function will do what a delta function does, which will force us to set k equal to p everywhere in our expression. Now let's just see what the implications of setting k equal to p are in any of our expressions on these omega factors. So we need to remember what the definitions of the omegas are. All that omega k is k squared plus m squared. Now, if in some expression, if we are actually using this commutator relation in an expression and we integrate and we've set k equal to p, this is then going to be the same as p squared plus m squared, which is of course our definition of omega p. So in practice, if we use this commutator anywhere, we're going to directly set k equal to p, and then through the definitions of the omegas also set omega k equal to omega p. Let's just check what happens with all of this stuff when we set omega k equal to omega p. Well, the exponential simplifies a lot because we have exponential of 0, 1. And then over the terms that remain, so let's write them out. So this omega p over 2, omega p 1 over omega k, this will go to, well, we'll set omega p equal to omega k. So when we take the square root, we'll get omega k over 2. And when we add 1 over omega k to 1 over omega k, we'll get 2 over omega k. So in other words, all of this stuff tends to 1. Okay, so in any actual expression where you will use this commutator, it is indeed the case that there is actually a nice result. You get this delta 3 k minus p. So that's how you go through commutator relations. So start by expanding A in terms of fields that you already know the commutator expressions are. You can then use some of the commutator identities. Use this one. You just then crunch through, simplifying as much as you can. When you get delta functions, you try and integrate them away. We integrated this one. We integrate it over y, work through the algebra. Remember your definitions of what delta functions are, unlike me, and I can't remember if it's a plus or minus, but it's of this form. It's a conventional choice, and I forgot my own convention. And then you work through. So when you end up with something that looks a little bit ugly, as we did here, and you're expecting something nice, it may be a sign that you have a little bit more work to do to actually end up with something nice, because normally you do end up with nice, simple expressions. Okay, so we've done one case. I believe in the problem sheet, you will also be able to show, you'll be asked to show the following other two results. So AK with AP and AK Tiger with AP Tiger, you'll be asked to show that both of these are equal to 0. So I'll leave that as an exercise for you to do in the problem sheets. Okay, so next we want to look at a very important quantity, the Hamiltonian. So we would like to express the Hamiltonian in terms of these raising and lowering operators. Okay, so just to remind you, so far the Hamiltonian that we have, so let me write down the full Hamiltonian. So that is, I'm going to include this d3x term, and not just the Hamiltonian density. But so far we have shown, or we've worked out, that this is pi squared plus the gradient of phi squared plus m squared phi squared. And in this canonical quantization procedure, we've turned all of these bits into, all of our fields into operators. But we have expressions for phi and for pi in terms of our creation and annihilation operators. So we should therefore be able to express h in terms of creation and annihilation operators. We have pi, we have phi, operators in terms of a, k, and a k dagger. Okay, so by substituting in for phi and pi into this expression, okay, in terms of our mode expansion, and let's not go through the full details, but if you were to work through the algebra, okay, so after working through probably a couple of pages of algebra, which is why I don't really want to go through it in this short course, because we've done one kind of commutation thing in detail. I'm not sure we have to do another one, but there'll be lots of pages of algebra, and we'll use some of those results we've just used. All right, so the AK AP dagger is 2 pi cubed. Okay, so let's imagine that we've gone through all of that. We would find following result. We would find that the Hamiltonian, so this is the total Hamiltonian, remember, not the density. Total Hamiltonian is an integral over, well, for some reason in my notes I've switched notation from k to p, but it doesn't really matter. We're integrating over the momentum modes. It's this dp3 2 pi cubed factor that we always get. We have an omega p factor. And then we have this following combination of operators. So a p dagger times ap plus then this funny combination of a commutator. So this, of course, is hopefully not a total surprise to you. I hope it was sort of what you might have been expecting, because in the simple harmonic quantum problem, our Hamiltonian looks like omega a dagger a plus a bit. Okay, so this is similar to what we have here. for each mode, we have an A dagger A, and then we have to sum over all the modes. So this is what this D3P factor is doing. And then we have the frequency for each mode. And then we have a contribution that comes from the 0-point energy. So this was the energy of the vacuum. So before it was simply a factor of a half. Here it's written as a half times this commutator of AP with AP dagger. Let's think about this term. It appears in a little bit more detail. So this bit is relatively straightforward, looks sensible, looks nice. This bit deserves a little bit more attention. What does this mean? Well, let's use the result that we've just derived a couple of minutes ago. So we looked at what A with AP was. AK with AP dagger. So this should be 2 pi. Well, actually, that's what it was. It was 2 pi cubed delta 3 K minus P. So it's not what we have in the expression above. In the expression above, we have E and P. We have to set K equal to P. Okay, so here we have this funny object, 2 pi cubed delta 3, 0. So we have, in other words, our Hamiltonian a little bit strange. We have a piece that looks fine, kind of what we were expecting, plus this weird bit that has a delta function evaluated at 0. Okay. So what's going on? So as I said, this bit looks fine. This is kind of what we were expecting, arguing in the fact that this Klein-Gordon field is a sum over an infinite number of harmonic oscillators. So we've got a term which has a sum over an infinite number of harmonic oscillators. But we've also got this kind of sum over an infinite number of 0-point energy pieces. So it's a little bit odd. So there's a problem, in principle, there's a problem with this term. Why is there a problem? Well, there's a problem because this delta 3, 0 is an infinite number. Okay, so this is the term it's associated with the ground state energy. On our normal simple harmonic problem, it was half, which is a nice number to deal with. Here, it's not 1/2, it's a half times an infinite number. So we see that this is telling us that the energy of the vacuum is not finite, so it's infinite. Okay, which is a bit odd. So in other words, the Hamiltonian acting on the vacuum, well, it's going to be D3P on 2 pi cubed. We're going to have omega P over 2 pi cubed delta 3, 0 acting on the vacuum. So this is an infinity. This delta 0 is an infinite number, and then we're integrating it from 0 to infinity. So no matter which way you slice it or dice it, you end up with an infinite number. So this is a problem. So there's different ways you can sort of resolve this problem. There's different ways that people argue it. So some people argue along the following lines. They argue that, well, it's fine to have kind of this base level of energies, which is infinite, because the only thing that's relevant are energy differences. If I have, an energy of infinity plus 2 and an energy of infinity plus 3, once I subtract off the difference between them, I end up with a finite contribution. And I guess this is known in other branches of physics where we have things like potentials and So we do this in physics, that sometimes it's only the energy, it's only differences of quantities that are actually physically observable. So the only problem with this argument is to do with gravity, because gravity should feel, well, all energy and mass gravitates. So gravity should feel if there's some infinite energy contribution thing there in the vacuum. So this would show up as a physical thing. It would show up as an infinite contribution to the cosmological constant. And we do not appear to live in a universe with an infinite cosmological constant. Okay, so somehow this infinity cannot really be there. Gravity is a problem. And gravity remains a problem because gravity doesn't just see the energy difference, it sees everything. That's one argument, but it's not entirely satisfactory because you still have something going to the cosmological constant problem. We can kind of tease it out a little bit further. Let's actually see what's going on, because there's really two infinities that are happening here. So there's one that comes from this delta function. Let's have a look at this delta function in more detail. Okay, so what's going on with the delta function? Well, we can think of it as the limit of the following expression. So it's L over 2. So it's old friend, the definition of an exponential in terms of exponents. So here, sign is positive. I think it is positive. Good. So this delta function is essentially measuring. Oh, and we also need to take, well, there's two things we need to do. So we are setting the limit that L goes to 0 to make it into a delta function. Then we've set 0. We've set p equal to 0. Okay. Otherwise, this would be the delta function at p. So we're setting the limit with two limits here. So when we set p equal to 0 in this exponent, we just get 1, and then we're just integrating 1 from minus L over 2 to L over 2. So what this is really doing is just telling us about the volume of this box that we're living in. Okay, so this 2 pi cubed delta 30 is just really a volume factor. And you might see this in other field theory calculations where people will write this as a volume factor just all the time. I think it also shows up in condensed matter physics and other bits where you have volumes appearing. But anyway, this infinite bit, the reason why this delta 30 is infinite is because we're considering an infinite volume of space. So we're making this approximation that we have an infinite box. So you could argue that, well, in reality, our universe isn't infinite. It has some finite size. So really, maybe the more physically relevant thing to consider isn't just the Hamiltonian, but actually you should divide our quantities by the volume of space. Okay? If we do that, divide out the volume factor, because although it's going to be very large, it should still be finite. Let's divide out this volume. So we're still going to have these other terms. We're just going to divide out the 2 pi cubed delta 30 terms. So we're still going to have d3p. Yes, the 2 pi cubed pieces. Then the omega p over 2 acting on the vacuum. You might think this looks slightly better. Let's see, I think I've actually carried one too many. Oh, no, that's fine. So yeah, this looks slightly better because we no longer have the infinite number appearing as we did here. However, we still end up with an infinite expression. And the reason we end up with an infinite expression is because we still have to do this integral over d3p, which is going to give us another infinity. Okay, so this is still going to be infinite because our p is still going to go not to 0. Our range from p goes from 0 to infinity. Okay, so in other words, our d3p is going to be some angle, but then there's a p squared dp bit. This still ranges from 0 up to infinity, and the omega p, so this will have the omega p factor, which has p squared plus m squared in it. Okay, so this is still going to be an integral which diverges, so it's still problematic. This is known as the UV infinity. This is diverging because we're considering very, very large values of p. Okay, so there is this problem that we have. Okay, we have this infinite term in the Hamiltonian. So what's the deal? Well, this is where step 5 of our recipe comes into play. So, see if you can remember what step 5 of our recipe was. So remember, we started by writing down the Lagrangian. We had to calculate pi and the Hamiltonian. We promoted things to fields and then imposed commutation relations. And then we expanded those fields in terms of correlation and annihilation operators. But then there was this final step, which was to apply the normal ordering procedure. So step 5 is all about this normal ordering. Let's discuss what normal ordering. Okay, so there is I've kind of discussed a couple of arguments here, or problems with the fact you get this infinity. But actually there's a way that you could quantize this theory without having an infinity appearing, quite straightforwardly. And that's because there's an ambiguity in the definition of the theory that we started with. So in particular, there's an ambiguity in the definition of the classical Hamiltonian. Let me tell you why there's this ambiguity. So we were using the classical Hamiltonian, let me call it H1, which was p squared over 2m. This is just the Hamiltonian for a single harmonic oscillator. So we have this Hamiltonian. But in the classical theory, the following Hamiltonian, write it down correctly, this Hamiltonian, where I complete the square of the Hamiltonian above, in the classical theory, these two Hamiltonians are completely equivalent. This is seems like a rather bizarre way of writing the above expression, but in the classical theory, all of these x's and p's just commute. So these, when you multiply the terms out, will give you exactly the expression above, and both are equally valid forms of the theory. Now, you'll remember that if I were to quantize this theory with my A and A dagger terms, so this product that I've written down here are exactly the form of my A and A dagger terms. If I quantize this H2 theory, this would lead to a Hamiltonian that does not have a 0-point energy. This would just lead to the following Hamiltonian, or rather, the following form. At the omega p, we would just have AP dagger AP. So we don't have, the infinity doesn't appear, the 0-point energy doesn't appear. But as I said, they're both the same classical theories. So why is it better to start with this one, H1, instead of H2? Is it just some aesthetic thing? The fact that we like it's a p squared over 2m, which we've seen written down 100 times, and we don't have the complex number appearing in it. But the point is that there is this ambiguity in going from classical to quantum theories, and they can lead to either having infinity or not having infinities appearing. So what's the point of this normal ordering then? So the point of this normal ordering is to remove any ambiguity that you have in going from the classical to the quantum theory. Okay, so this is why we apply it. We got this problem. Or at least this is the aim of what normal ordering in. This is the aim of what normal ordering will do, remove this ambiguity. So let me tell you what it actually does and how it does it. What normal ordering in practice does is that it moves all of my annihilation operators, all of my A sub k operators, it moves them all to the right-hand side of the expression. Okay? So the notation we use is that we write either n, the fields that we want to normally order written beside the n, or many books use this funny double colon structure. Let me give you an example. If we want to do the normal ordering of the following product, so let's do A dagger, A dagger. Okay. This is equivalent to this notation with the double dots. And so what it does is this will move my annihilation operators to the right. So I'll end up with A dagger, A dagger, A. Okay, so this is what it means. Normal ordered version is A dagger, A dagger, A. Okay, so what we can then do is apply this normal ordering procedure. We can apply but apply to the real scalar field. Okay, so or at least the Hamiltonian that we got from the real scalar field. So the normal ordering of the Hamiltonian that we find is going to be, let's write down that are not operators, because the normal ordering only concerns itself with the operators. So we have E, we have the omega p term, and then we're going to do normal ordering on the AP dagger, AP, plus, let's write it as the commutator of AP with AP dagger. Okay, and we can just apply the normal ordering term by term. So n on AP dagger, AP leaves it unchanged because my annihilation operator is already to the right. But when I do it on this commutator, well, let's see what happens by writing out what the commutator is. So it's AP dagger minus AP dagger, AP. So the normal ordering will move my annihilation operator to the right. So I'll get AP dagger, AP minus AP dagger, AP, which is 0. Okay, so in other words, this normal ordered Hamiltonian is the Hamiltonian, but without this infinity problem we had before. So it has removed in a sort of systematic, controllable way this delta function term that was appearing, that was giving rise giving rise to this problematic infinity that we were unsure of how to interpret. So with the normal ordering, we don't even have to think about it because it's just been removed from the problem. Let's end this lecture then with a very brief summary. So we have found all of the useful commutation relations for this theory. So we've got the commutation relationships between the pi and the phi fields, and expressing or inverting the relations between I, phi, A, and A dagger. We derived the bottom relationships between the A, the annihilation and creation operators, and in the problem sheets you'll work out these two. What else did we do? Well, we found the Hamiltonian for this theory. So we find a piece that was kind of as we expected, but we had this slightly problematic piece that gives rise to an infinite contribution to the ground state energy. So we discussed that a little bit and why it's potentially a problem. But then we discussed a procedure that we invoke in this canonical quantization procedure, which is the normal ordering process. So the normal ordering removes this infinite term. It does this through the operation of moving all of my annihilation operators to the right in an expression. So this act of moving things to the right in the expression gets rid of the problematic commutator term in the above expression.